The primary design goal for an EV battery pack is to house thousands of individual cells within a sealed enclosure to maximize volumetric energy density. This enclosure must simultaneously manage a complex set of internal physical forces that arise during the battery's normal operation. During every charge and discharge cycle, lithium-ion cells physically expand and contract, exerting continuous structural pressure against the surrounding framework. Pushing high-voltage current through dissimilar metals generates localized thermal expansion, creating mechanical stress at electrical junction points. The system is also engineered to handle extreme scenarios, such as the rapid generation of high-velocity toxic gases during a cell failure. To understand how these forces are managed, we will examine the pack's construction starting from the micro level of a single cell up to the macro level of chassis integration. Effective battery packaging is defined by the ability to contain and regulate these mechanical and thermal changes over a 10-year operational lifespan. Lithium-ion cells swell as they age from gas generation and SEI layer growth. Engineers provide a swelling allowance, typically a 3 to 8% volume increase. Yet cells must be held within a strict 5 to 15 kilopascal compression range to maintain internal chemistry. If compression drops below 5 kilopascals, the internal electrodes can delaminate. If it exceeds 15 kilopascals, the resulting pressure can cause irreversible damage to the cell separator. Maintaining this pressure window over thousands of cycles requires an active mechanical housing rather than a simple frame. Rigid end plates and wave springs are integrated into the module to apply a constant, calculated inward force against the expanding cells. Between individual cells, elastomer foam spacer pads are used to absorb daily micro-expansions and maintain uniform pressure. These foam pads are subject to relaxation, meaning they lose stiffness over time. To ensure long-term reliability, they undergo 1,000-hour compression testing at 60 degrees Celsius to simulate years of aging. The module housing functions as a calibrated vise, specifically designed to counteract the electrochemical aging of the cells. High-voltage interconnects, or busbars, are required to route current loads that often reach between 200 and 800 amps. High current flow generates heat. As temperatures rise, metallic components expand at different rates. This mismatch in the coefficient of thermal expansion means copper expands at 17 parts per million per degree Celsius, while the aluminum housing expands at 23. During a 60-degree temperature shift, these metals pull in opposing directions. In a rigid system, this stress shears weld joints and loosens terminal bolts. Design solutions involve replacing rigid bars with flexible components, such as laminated bus bars or braided copper connectors. Engineers often use S-shaped expansion loops. This geometry allows the bus bar to flex and absorb lateral thermal strain without exerting force on the weld joints. To secure these connections, Belleville washers act as heavy-duty springs, maintaining a constant clamping force on bolts, even as the surrounding metals expand and contract. Reliable electrical continuity requires treating solid metal interconnects as elastic parts that must shift with temperature changes. If a cell enters thermal runaway, the engineering priority shifts from efficiency to the immediate safety of the passengers. A runaway event rapidly releases hydrogen, carbon monoxide, toxic hydrogen fluoride, and flammable vapors. This creates a sudden and violent pressure spike within the rigidly sealed battery enclosure. Engineers use computational fluid dynamics to calculate burst pressure against gas generation rates, designing specific internal paths to route gas safely. Top-mounted vents with one-way rupture membranes control the exhaust, while flame arrestor meshes prevent ignition. Directional ducting ensures these explosive gases are channeled away from the passenger compartment and any potential reignition zones. Beyond gas management, the housing must prevent thermal propagation, the spread of heat from one failing module to its neighbors. Safety standards such as AIS 156 require the pack to delay adjacent cell ignition for at least 5 minutes to allow for vehicle evacuation. Isolation is achieved using specialized materials like aerogel insulation, ceramic barriers, and mica sheets between modules. Controlling a thermal runaway event requires a combination of designed weak points and precise gas routing geometry. At the vehicle level, the battery pack must also withstand external environmental stresses, including rapid changes in atmospheric pressure. Because the pack is sealed, driving to a high altitude creates a pressure differential between the interior and the ambient air. If unmanaged, This difference can compromise the protective gaskets. Breathable membranes and one-way valves allow the pack to equalize internal pressure with the atmosphere without allowing moisture to enter the enclosure. Over a longer timeline, the aluminum housing is subject to a phenomenon known as material creep. Years of internal module pressure, thermal cycling, and road vibration cause the aluminum baseplate to slowly deform. Engineers use long-duration finite element analysis to predict this deformation and add reinforcing ribs to the casting to maintain structural integrity. The mass and rigidity of the pack also affect vehicle acoustics. A large, flat battery enclosure can amplify low-frequency vibrations from the driveline into the cabin. To prevent this, damping pads, foam layers, and isolated mounting points are used to acoustically decouple the pack from the chassis. Long-term reliability depends on the pack's ability to adapt to atmospheric changes and resist years of structural fatigue. Integrating these requirements, from compression padding to gas venting, requires extreme manufacturing tolerances. Engineers perform stack-up analysis to ensure that minor variations at the cell level, as small as 0.3 millimeters, do not lead to a structural failure at the housing level. Modern workflows utilize a digital twin to simulate thermal maps, gas routing, and structural tolerances simultaneously before any physical components are manufactured. This process begins with cells that physically change volume as they age. It includes high-voltage busbars that expand and contract with every surge of current. It requires a housing that can safely manage the pressure of a catastrophic failure. And it results in a reinforced shell that equalizes pressure while resisting a decade of road vibration. EV battery packaging ensures long-term safety by containing the volatile physical behavior of energy storage within a precision-engineered structural system.